Hello, I'm Seth Kessler, President and CEO of the Metis Design Corporation. This Tech Talk will provide a high-level summary of our NAVAIR STTR project in collaboration with MIT for developing nano-engineered aligned interlaminar scaffolding, or NAILS, as reinforcement for composite rotorcraft components. Metis Design is a small technical consulting firm located in Boston, Massachusetts. We specialize in structural health monitoring technologies and nano-engineered multifunctional assemblies. We have experience from more than 24 Phase 2 SBIR efforts, many of which have resulted in successful commercialization, including technology licenses to Tier 1 suppliers and spin-off companies. Presently, we are exploring the formation of a new entity in part to convey the NAILS technology I will be describing in this Tech Talk. Composite materials are increasingly being used in defense and aerospace applications due to their ability to reduce weight without sacrificing strength, as well as their resistance to corrosion and fatigue. The Achilles heel of composite materials, however, is their interlaminar strength. They are very robust in plane, but with only epoxy holding adjacent layers together, they are susceptible to delamination. This problem is further exacerbated for critical rotorcraft components that employ ply drops to taper their thickness, as those result in even larger resin-rich regions between the adjacent plies. The goal of this STTR was to improve the interlaminar strength by at least 10% and improve the fatigue life by a factor of 2, specifically targeting the CH53K flex beam. Under this STTR, in collaboration with MIT, we invented nano-engineered aligned interlaminar scaffolding, or NAILS. The basic concept is that we have engineered a network of nanofibers that fill the resin-rich region between plies and will not increase the interlaminar thickness or adversely affect resin flow during composite cure. Locally, these nanofibers create a polymer nanocomposite, or PNC, with their principal strength being oriented perpendicular to that of the adjacent plies, specifically in the through thickness direction of the laminate. At the time the slide was created, we were using vertically aligned carbon nanotubes as nails, but subsequently we have also demonstrated equivalent performance with alternative, lower-cost nanoscale fibers. During the Phase 1 effort, we integrated nails into short beam shear specimens in order to optimize the placement and density of nails. The best configuration resulted in a static strength consistently 15% higher than unreinforced baseline specimens, which ultimately resulted in a 5 times improvement in fatigue life measured at multiple load levels. During the Phase 2 base period, which was completed after these slides were prepared, tapered specimens were tested that were designed to be representative of scaled flex beams under an appropriate loading configuration. Using both the CNT-based nails and a nylon-based alternative, a static strength increase of 25% was demonstrated over unreinforced baseline specimen. The fatigue life was increased by at least 5 times using a nylon nails. However, most of these specimens did not fail during the duration of the test and were stopped at 3 million cycles. And those that did fail, failed at the grips as opposed to delamination of the reinforced interlaminar region. Presently, this technology is roughly at a TRL and MRL of 4, having conducted scaled testing with representative commercially available materials. If the Phase 2 option is elected this spring, we will work together with Sikorsky to increase the TRL to 6 by applying nails to a full-scale flex beam test over the course of the next year. In summary, nails is a nano-engineered layer that is able to be strategically applied to reinforce the interlaminar toughness of any composite laminate. Nails is compatible with standard composite prepreg and manufacturing processes and can be applied as a tape or a veil. Results to date have shown consistent static interlaminar strength gains of 15 to 25%, with fatigue life extension greater than a factor of 5. These improvements would translate to increased maneuverability and/or payload capability for rotorcraft, in addition to extending the usable life of critical and expensive rotorcraft components. We are seeking additional programs of record who might be interested in exploring using nails to strategically improve their critical composite components. I would also like to highlight some of our other work with nanoengineered layers, including reinforcement of high-temperature composites such as polyimide and thermoplastics, in addition to resistive heating for de-icing and out-of-oven composite manufacture, all using carbon nanotubes. Again, I thank you for your attention, and please contact me directly if you'd like further information about any of the innovations I've presented today.